Grade 12 Physics, Quantum Mechanics, Note number 2, the photoelectric effect. The photoelectric effect is our main piece of evidence that light can behave as a particle as opposed to a wave. I'll explain the effect in a second, but right off the bat, it was actually discovered by a physicist, Philip Leonard, but it was Albert Einstein who was actually able to explain the particle nature of light, and that's actually what Einstein won his Nobel Prize for. Basically what this experiment is if we get a piece of metal, we can shine light onto that metal. If we shine the light on that metal with a high enough frequency, so a light that's more towards the blue or the purple end of the spectrum, we notice that electrons end up getting kicked off of that piece of metal. Again, if we shine light with a high enough frequency on this metal, we're able to eject electrons. The way light is acting on this metal is sort of like a momentum collision, like a billiard ball coming in and knocking electrons off of that metal. The main feature of that light that actually kicks the electrons off is its frequency. The energy associated with that frequency energizes one of those electrons. Some work is needed to dig that electron out, and whatever energy is left over is going to be the kinetic energy of that electron. The only way to explain this is if light is acting as a particle, not as a wave. It's the frequency or the energy of the light that's the determining factor, not the intensity or the amplitude. If we actually want to calculate the kinetic energy of those ejected electrons, we can treat this as a conservation of energy problem, where some energy is lost along the way as work. We know our initial energy is that light energy, our new equation that we learned equals hf. We're going to lose a little bit to dig that electron out as work, and whatever energy is left over is going to be kinetic energy. So we're going to have hf minus w equals ek. If we rearrange this equation for kinetic energy, we're going to get ek equals hf minus w. This is an equation we can use to actually calculate the kinetic energy of the ejected electrons. Here ek is in joules, h is our new value, it's our Planck's constant, f is the frequency of the incident light, and w is the work function to dig out the electron. Work function is actually going to be given in a new unit of energy called an electron volt. All we need to remember is that an electron volt, 1 electron volt is 1.6 times 10 to the negative 19 joules. So let's do an example. Let's say violet light with a wavelength of 425 nanometers is shining on a piece of sodium. And to dig 1 electron out for sodium, it's going to require 2.36 electron volts. Let's calculate the kinetic energy of those ejected electrons. So we'll get out our new formula. First we need to insert the frequency, but they gave us a wavelength, so let's make this conversion, putting it into the universal wave formula. We get 7.06 times 10 to the 14 hertz. We also need to put in a proper work function in joules. So here if it's 2.36, we just multiply that with 1.6 times 10 to the negative 19, and that should give us our correct work function. After inserting all the numbers, we should calculate that the ejected electron kinetic energy should be 9.02 times 10 to the negative 20 joules. If we actually want to calculate how fast that is, we know it's a kinetic energy, so we can use the kinetic energy formula just to calculate a velocity. So rearranging for velocity, we're going to put in our numbers, our energy being what we just calculated, and the mass of an electron, 9.1 times 10 to the negative 31. We're going to find that these electrons are going to be going 4.45 times 10 to the 5 meters per second. Einstein theoretically came up with this, but every experimental physicist always wants to verify a theory in the lab. Here Millikan, and among a lot of others, he was among a lot of other scientists of the day, really thinking that light was actually and had to be a wave, and there was no possible way it could be a particle. So Millikan tested Einstein's theory. I'm going to show you the results of his tests, but first we need to realize how closely our kinetic energy formula looks like the equation for a straight line, where each of those variables play a different role of y equals mx plus b. So Millikan did the photoelectric experiment on different metals, and he measured the results. He wanted to compare the frequency of the light that is shined on the metal with the kinetic energy of the ejected electrons. First he did it with potassium. He noticed that as he increased the frequency of the light on this piece of potassium, the ejected electron kinetic energy also increased. He did this with sodium, which ended up all being at higher frequencies, and he also did it with zinc. These are the three metals we're going to look at. The first thing he noticed is all three of these lines were parallel. When he actually went to calculate the slope of those lines, the slope was exactly equal to Planck's constant, 6.626 times 10 to the negative 34. When the lines were extrapolated back to the y-axis, he noticed also that each of the intercepts along the y-axis were exactly equal to the work functions for those metals. Everything he did, everything he measured, showed the linearness of that equation. He also noticed that where they intercepted the x-axis, those were called the threshold frequencies, or the minimum frequency needed to make the photoelectric effect work. Millikan basically verified Einstein's theory.